Hello students, and welcome. Today we are going to tackle a very important topic from our Unit 4, Moving Charges and Magnetism, and that is Ampere's Circuital Law. Now don't worry about the name. We are going to break it down in such a simple way that you will understand it properly, remember it for your exams, and hopefully score full marks. So let's begin.
So, y'all remember the Biot-Savart law, right? We use it to find the magnetic field. But you've probably noticed that sometimes, well, most of the time, the integrations can get very, very complicated. It takes a lot of calculation. So it makes you wonder, doesn't it? Is there a shortcut? Is there an easier way to do this?
And the answer, thankfully, is yes. You see, on one hand, we have the long road. That's the Biot-Savart law with all its tough integration. But on the other hand, we have a fantastic shortcut, Ampere's Circuital law. Think of it as an elegant, clever tool that uses symmetry to make our calculations much, much simpler.
And here's the best way to think about it. This should sound very familiar to you. Just think back to electrostatics. Remember how Gauss's law was a brilliant shortcut for Coulomb's law, but only in situations with a lot of symmetry? Well, it's the exact same idea here. Ampere's law is the magnetostatics version of Gauss's law. So, you see, you already understand the basic concept.
Okay, so let's get to the official definition, the one you need to write in your exams word for word. According to our NCERT textbook, Ampere's Circuital law states that the line integral of the magnetic field around any closed loop is equal to mu naught times the total current passing through that loop. And the formula, which you have to remember, is the closed loop integral of B dot dl equals mu naught times I.
This diagram here shows the idea perfectly. Look, we have some imaginary closed loop. You can think of it like a boundary. And we have some currents that are passing through the surface that is formed by this loop. Now what Ampere's law does is it creates a connection, a link, between the magnetic field that exists on this boundary and the total current that is piercing through the surface. It's a relationship between what's on the edge and what's going through the middle. Let's just quickly break down this formula so there's absolutely no confusion. That little circle on the integral sign simply means we're summing up over a closed loop. We're going all the way around. B dot dl is basically the piece of the magnetic field that's parallel to our path, and we add it all up. On the right side, I is the net current inside our loop, and mu zero, well, that's just a constant, the permeability of free space. Simple, not? Okay, theory is one thing, but let's see how this law actually works. We're going to take a classic, very common exam question, finding the magnetic field of a long, straight wire carrying a current. This is where Ampere's law truly becomes our best friend. Right, so the first and most important step is to choose an imaginary loop. We give it a special name, an Amperian loop. Now, the whole trick, the secret, is to choose a loop that perfectly matches the symmetry of the current. For a long, straight wire, what's the most symmetrical shape you can draw around it? A circle, of course. So we'll draw a nice circular Amperian loop of radius r centered on the wire. Now you just have to follow these 4 simple steps. Step 1, we've chosen our symmetrical loop, a circle. Step 2, let's calculate the left-hand side, that scary-looking integral of B dot dl. Because of our clever choice of a circle, the magnetic field B has the same strength everywhere on the loop, and it's always parallel to the loop. So the integral just simplifies to B multiplied by the circumference of the circle, which is 2 pi r. See? The integration is gone. Step 3, find the right-hand side. Well, the total current passing through our loop is just I, so the RHS is mu 0 I. And finally, step 4, just equate the two sides. B times 2 pi r equals mu 0 I. That's it. And just by rearranging that super simple equation, we get our final answer. The magnetic field, B, is equal to mu 0 I divided by 2 pi r. Now this is the exact same result you'd get from the Biot-Savart law, but you'd have to do pages of difficult integration. Here, we did it in just a few logical steps. This is the real power of Ampere's law. Let's just do a tiny example to see how easy this is. Let's say the current, I, is 2 amps, and we want to find the field at a distance r of 0.1 meters. We just have to plug these values into our shiny new formula. We know that the constant mu 0 divided by 2 pi is just 2 into 10 to the power of minus 7. So B becomes 2 times 10 to the minus 7 times 2 divided by 0.1, which gives us 4 times 10 to the minus 6 Tesla. It really is that straightforward.
Okay, now for a very, very important section, let's talk about some common exam mistakes.
I like to call these silent killers because they are small misunderstandings that can cause you to lose marks without even realizing it. Let's make sure you don't fall into these traps.
So this is probably the biggest point of confusion for students. You look at the formula, you see the loop, and you ask, does this letter I stand for a current that is flowing in the Amperian loop itself?
And the answer is a very, very big no. Please, everyone remember this. The Amperian loop is just an imaginary path we draw in space. It's a mathematical tool. There is no actual wire or current flowing along this loop. The I in the formula is the real physical current that is piercing through or threading through the area that is enclosed by our imaginary loop. This is a crucial distinction.
Okay, next common question. Since Ampere's law is so simple and so powerful, should we just forget about Biot-Savart law completely? Can we just use this for every single problem?
Now this is a very important point of clarity. Ampere's law is always true. For any closed loop and any steady current, it holds. It is a fundamental law of physics. But it is only useful for us to calculate the magnetic field when the problem has a very high degree of symmetry. For situations like a long straight wire or a solenoid or a toroid, it's a lifesaver. But if you have a wire of a finite length or some random shape, the calculation becomes impossible, and then we have to go back to our old friend, the Biot-Savart law.
So, let's just zoom out for a moment and connect the dots. Let's see the bigger picture of where Ampere's law actually fits into the grand story of physics.
And this table just makes that connection so clear. Look at the beautiful pattern. In electrostatics, your fundamental law was Coulomb's law, and your shortcut for symmetric cases was Gauss's law. Now in magnetostatics, your fundamental law is Biot-Savart, and your shortcut for symmetric cases is Ampere's law. And what is the key to using both of these powerful shortcuts? It's the same thing, symmetry. This is a wonderful way to remember the whole idea.
All right, so to quickly summarize, here are the key points you must take away for your exams. First, Ampere's law connects the magnetic field on a closed loop to the current that passes through it. Second, the formula integral of B.dl is mu naught I. Third, it's a massive shortcut, but only for symmetrical problems. Fourth, for a long straight wire, the result is B equals mu naught I by 2 pi r. And finally, remember, the law is always true for steady currents, but it's only useful in those special symmetric cases. If you remember these 5 points, you are all set.
So we have seen that Ampere's law works perfectly as long as the currents are steady and constant. But in physics, we always have to ask, what if? So I'll leave you with a question to think about. What happens if the current is not steady? What if the current is changing with time? Does our beautiful law still work, or does something new and even more fascinating happen? We'll explore that question next time.